Well, in the last module, we obtained the infinitesimal change in the value of a scalar field dt, where t, we took temperature as an example of a scalar field. A scalar field, by the way, is a field whose value at any given point in space or time does not depend upon the choice of the coordinate system, unlike a vector field whose value adds values at different points might depend upon the underlying coordinate system. So just to continue with the example that we've been working with so far, we took temperature as an example of a scalar field, and we motivated it using the example of an air conditioner unit running in a room, and you go at different location or different points of the room to measure the temperature. Now you can also define a vector field in the same room. Let's say you have the air conditioning might have a wind blowing unit attached to it. And if you measure the wind velocity at different points in the room, that would constitute a vector field. So we'll come back to examples of vector field in a future video, but for now we'll focus solely on scalar fields. So in order to calculate the total change, or rather the infinitesimal total change in the value of temperature, as you move from a point, say x, y, z, to a neighboring point, x plus del x, y plus del y, z plus del z, we express that total change in the form of the del operator operating on the scalar field and dotting it with the infinitesimal change in the coordinate, in the position coordinate that you've decided to measure locations in the room with. Now, this del operator, when it operates on the scalar field, is what we define as the gradient of a scalar field. So this is perhaps this constitutes the first example of a higher dimensional derivative which we have been building our way up to so far, which is the gradient of a scalar field. Now, just like the ordinary derivative, which we reviewed in a previous module, which measures the slope of a function at different points, does the gradient also have a physical and a geometrical interpretation? So let's explore this idea a little further. Imagine that you were to measure the total change in the value of the temperature, right? Rather, the infinitesimal total change in the value of the temperature as you move from one point to a neighboring point. Now, if you recall the definition of a dot product, this total change, which is the dot product of del t, which is the gradient of t with the unit or with the infinitesimal position vector dr, can be expressed in the form of modulus of the gradient times the modulus of dr times cosine of the angle between the two vectors, gradient vector and the position vector. Remember, the gradient of a scalar field itself is a vector. So the field we are talking about, the temperature, is a scalar, but when you calculate its gradient, you obtain a vector. And we'll sort of prove this point in a future video, that when you use the del operator and operate it on a scalar field, you end up constructing a new kind of a vector. But before we get to that, let's take it for granted that the gradient is a vector. When you dot it with the position, you obtain the total change in the value of the scalar field. And the dot product itself can be written as the magnitude of the gradient times the magnitude of the change in the position vector times the cosine of the angle theta. Now let's, for simplicity, focus our attention onto a two-dimensional plane. And let's say you're at some point x, comma y, where you've measured the temperature. Now from this point onwards, you take tiny steps of the same magnitude in different directions. So for instance, you might be here and you take one tiny step, say in this direction. You take another step in this direction, you take another step in this direction. And as you move in these different directions, you measure the temperature at these new locations. So you measure the temperature here, you measure the temperature here, you measure the temperature here. And let me just label this as T prime. And you calculate the difference between T prime and T, which is what your original location was. Now there'll be one particular choice of direction, perhaps this direction, which will coincide with the direction of the gradient vector. Remember, the gradient is a vector, so it'll have both a magnitude and a direction. And there'll be one direction which will coincide with the direction of the gradient. That direction, along that direction, we'll find that the change in the value of the temperature is the highest. And the reason that is the case is because if I fix dr, if I fix the magnitude of the steps I'm taking in different directions, then this magnitude is fixed. And as you move in different directions, the only thing you're changing is the cosine of the angle, or rather the angle that the gradient vector makes with the position vector. So as I move in this different direction, as I take steps in these different directions, there'll be one direction which will coincide with the gradient. When we say that this direction coincides with the gradient, what we mean is that along that direction, theta is 0. Remember, when we take the dot product between two vectors, say we have a vector A and a vector B, and they make an angle theta between them, there's one direction. If I'm saying that that you're moving in a direction which coincides with the direction A, it means that I'm sort of stepping in the same direction as the direction A, which means theta is 0. And in this direction, or along this direction, cosine of theta is 1, which is the highest value that it can assume. So in other words, the gradient vector points in a direction where the change in the value of the function, change in the value of the scalar field is the highest. Or in other words, it's the direction of maximum ascent. Conversely, if I move in a direction opposite to that of the gradient, you move in the direction of highest descent. In fact, this is the idea which is used in many optimization and machine learning algorithms, where you calculate the gradient of an underlying scalar field and move in a direction which is opposite to the gradient. And this is called the gradient descent algorithm. So just to summarize, the gradient has a direction, and that direction is the direction along which the change in the value of the scalar field is the highest. So I have a gradient, you have its magnitude. So this is the magnitude. I'll come to what it means. And then you have the direction of gradient of t. And this is where the change in t is highest, or this is the direction of maximum ascent. Now, if I go back to what the magnitude of gradient of t is, notice that if I look at this expression, dt equals magnitude of gradient of t times magnitude of dr times cosine theta, and let's say theta is 0, so cosine theta is 1, then gradient of t is the change in t divided by mod of dr. And this reminds us of the definition of an ordinary derivative. So in other words, the magnitude is the slope. The magnitude of the gradient is a slope along the direction of maximum ascent. So the gradient is a vector. It has a magnitude and a direction. The direction is that direction where the change in the value of t is the highest, and the magnitude is the slope along that highest direction. Just as a quick exercise before we go on to before we sort of build onto this module in a future video, try and think of what happens if you move in a direction where theta is 90 degrees. Conversely, what about isolated points where gradient itself is 0? What could be the physical interpretation behind these points? So let's build on these ideas in future videos. I'll upload a quiz as the next part of this particular module, and give it a shot. If you have any doubts, feel free to book a one-to-one consultation with me through the website, and be happy to answer your questions. Thanks for watching.